Now it's time to analyze the thermal efficiency of the Brayton cycle, the ideal closed one, with all the assumptions we said in the first video, in the very first one. So we know already that the thermal efficiency of any cycle equals what we get for what we pay. What we get is the work out, the work net out, and what we pay is the Q in. The Q out is considered as the byproduct. It's something that we dispose in order to complete the cycle. It's not there in the actual one, but we have the Q in the actual one. This is what I pay. This is what I get into the cycle, and this is what I pay and I get into the cycle. What I get out of the cycle is the net work output. Doing the first law analysis, we know that the Q in minus Q out equal to the net work that I get over Qn, which is 1 minus Q out over Qn. From analyzing the cycle itself, we have come to these laws. Qn equals Cp T3 minus T2, Q out equals Cp T4 minus T1, the same which was originally H3 minus H2, and this one was H4 minus H1, and both processes are at constant pressure. And this one we get from the analysis of process 1 to 2 and 3 to 4, where Rp is the pressure ratio and K is the ratio between the specific heats, Cp over Cv. Thus, we substitute by these laws in here, and we get 1. Excuse me. Need some space, so we're gonna move this a little bit up. 1 minus Q out Cp over Cp. These two cancels out. We're left with 4 pressures. Q out is T4 minus T1. T4 minus T1. And Qn is T3 minus T2. Taking Q1 as a common factor from the numerator, we are left with T1 over T2 times T4 over T1 minus 1 over T3 over T2 minus 1. From this law, we can detect that since T1 over T2 equals T4 over T3, then T3 over T2 is equal to T4 over T1 from the proportionality laws. And subtracting 1 from both sides, those two quantities are the same. We're left with 1 minus T1 over T2. This is the thermal efficiency of the Brayton cycle. 1 over T2. Yes, 1 over T1 over T2. And we already knew that Rp, T1 over T2 equals pressure ratio is to the power 1 minus K over K. Thus, this one equals 1 minus Rp to the power 1 minus K over K. And the K is always greater than 1. It's always written as 1 minus 1 over Rp to the power K minus 1 over K. To illustrate the inverse, the direct relation between pressure ratio and the thermal efficiency. Thus, we know that the thermal efficiency is directly proportional with Rp to some power m, which is always positive. I knew that this relation is a direct relation. Okay, and its graph looks like this. We will need the other portion of the graph in a minute. Looks something like this. Rp against the thermal efficiency. Some range over here is the practical region for some design and considerations, which varies between 5 and 20 pressure ratios. Okay, thus we came to a conclusion, a false conclusion, that as we increase the pressure ratio, the thermal efficiency also increases. But that's not true. That's not totally true. Because as the thermal efficiency increases, as the pressure ratio increases, the net work that I get out of the system decreases. So the relation between the net work output and the pressure ratio is not direct. It's somewhat complicated relation between them. Let's look something like this. And it's also important to handle that these drawings are not to scale, it's just for this illustration. And this one especially depends on the temperature ratio, which is T3 over T1, the maximum temperature and the minimum temperature. We have already agreed that the maximum temperature is the limiting temperature. This temperature limits me in the design that if I go further above, my turbine blades might be pitting, anything might be wrong with my design, and my materials will not withstand temperatures above this limit. Thus, we need to compromise between having a high efficiency, using less fuel, and obtaining work net using the same amount of circulating fluid. But increasing the work net, when I need to increase the network output, I need to increase the circulating work, because all of these analyses are based on a unit mass basis, are normalized for the mass. So all the quantities we calculate over here are small ones. This should be made earlier on, sorry, but this all the small letters in most of the thermodynamic books indicate quantities on a mass basis. The enthalpy per unit mass, the work per unit mass, and so on, all the analysis. Thus, we have to make some compromise between both the efficiency and the output work. And to visualize and to be convinced with this argument, we might make a somewhat graphical argument to discuss this matter. We already agreed that the thermal efficiency equals 1 minus 1 over RP over T minus 1 over K. This is we have derived already. Looking at the two graphs over there, the PV and the TS. Let's first look at the TS. I have a limiting temperature, which I can't go beyond, which is T3. And I take intake fresh air from the atmosphere. So over here, the pressure is atmospheric pressure, and the temperature is ambient. So this point is 1. I have to draw some constant pressure lines to work between. Assume that those are almost constant pressure. There is not to scale, and this drawing is also just for illustration. So if I'm working between these two, my cycle would look like something like this. If I'm working between these two, I know that this process has to be isentropic, and this process has to be isentropic, isobaric, and isobaric. This one might be something like this. And this one something like this. Another one over here might be something like this. We have agreed from the very first beginning that the area included in the PV diagram, based on our assumptions, is the work that we get out of the cycle. And also, this area over here is the difference for a reversible cycle, is the Q. Both areas are equal to the work net, which is equal to the Q net. This one is the work. We are all convinced with this, that the area included in the PV diagram for a reversible ideal process is the work output. And this one, TS diagram, from the second law, we know that this area included is also the cube, whereas there is no entropy generation. Great. Thus, when we aim at maximizing the W net, we aim at maximizing this area. We will notice that this area is small, gets bigger, bigger, and then gets smaller again. Indeed, this area is smaller than this area. This one, let's change the color to be more obvious. This one is indeed smaller than this one. And this one is also small. Thus, at some point in between, for a certain pressure ratio, and the ratio between these lines is the pressure ratio. If this is P1, and this is, all these points are 3, point 3, 3 dash, 3 double dash, 3 triple dash. Thus, at some point here on the drawing, it's 3 double dash, where P1 over for a minute, it's P3 double dash over P1 is the pressure ratio. Thus, for some pressure ratio, I have the maximum work output, which peaks and then goes down. Now let's make a similar argument on the PV diagram. You have the PV diagram. We know that our limit is between two temperatures. So we draw our two isotherms. This is T3 and this is T1. Where T1 intersects with atmospheric pressure. This is our point 1 where we start. So the cycle might look like something like this. So this is not sorry, this is wrong. This cycle, we know that it's isentropic, so the isentropic process looks like something like this. Like this, and like this. I've already agreed that the isotherms is more steep or more curvy than the isotherms. So this might look like something like this, or like this. Also, maybe like this, or like this. We again notice that there is some process in the middle where the area included in this graph is maximum. So it's small, it's larger, and then gets small again. So we might compromise for the net work output of something like this cycle in the middle. Applying those graphical arguments, we are now convinced that these two might be our constraints, our design constraints, on the basic level, at least on the basic theoretical level, that those two are our design constraints, and given another parameters and the design constraints, the atmosphere, the working conditions, and so on, and things discussed in the propulsion, jet propulsion courses and other courses, we might get a compromise between these two to compromise between the network output and thermal efficiency of the cycle. Compromising the efficiency of the cycle gets me use less fuel, and the compromising for the net work output gets more work output out of the cycle. So I need more, and I need to compromise between them. Thank you.